So we're carrying on looking at rings. In many ways, rings can be thought of as a data structure, as a safer way of using arrays in computer programming languages. The advantage of rings is very difficult to make them crash. You can make them crash, but it's very difficult to do. And usually it's because you've misspelled something, or you've put the wrong data item in there, and it's actually the rings that haven't crashed. It's actually the value that you're passing to something to do. We can use rings just as they are, but Sonic Pi actually lets you do lots of different things with rings. I mean, what Sam Aaron has been able to do is essentially extend the idea of rings into lots of usable data structures, so that you don't have to keep redefining them in some way. They're already defined in Sonic Pi. So let's have a look at some of those. So we've looked at rings, and rings can be thought of containers, let's say for notes. Let's say that we're just holding notes in those rings. So a development of that sort of ring idea of holding notes is the scale. So it has a defined ring that is called scale. Let's call it my scale. So that's the variable name. My scale equals, open brackets, and then when we press scale, we can see the sort of autocomplete sort of come up here. So for scales, we define the pitch of them. So let's say that we want, and this will give us also the kind of the register that we want it to be in. So let's say we want it to be C4. And then we have a comma. And then we can define a type of scale. So you can see here, lots of different types of scales that could be used here. I mean, it's tons. Right? So notice that each of these scales, they start with a full colon. So they're an object, much like the C4. So let's say we're going to use major. So we get a number of majors, major pentatonic. Let's say we use major. This will give us a 1-octave major scale. But what we can also do is specify a number of octaves. So this is the num underscore octaves, followed by a colon, space, and then a number. Let's say we want 2. So we're going to have a 2-octave scale, right? So look at the format of that. Variable name equals, open the brackets. What kind of entity is this? It's a scale, right? So a scale will have, basically has a number of parameters attached to it. We have a pitch, so we're going to say C4, which gives us an octave that it's working from, starting at. A tonality, major, and then the number of octaves we want. Let's say we want 2 octaves. So, live loop, scale player. Let's make a sleep value 0.5. And then we do play my scale top tick. I've just realized I've misspelled octaves. You see, this is how safe rings are. It didn't even crash, even though I'd misspelled octaves. Let's try that again, shall we? Let me just get the release values down here, 0.2. And let's change the register to 3. And so on. You can make it 5. Let's say we start from C1. It's quite low. So you get the idea. So that's a scale. So we've looked at rings as containers for selections of notes. We've also looked at rings with a specific kind of purpose, scale. So there are of course other ones that operate in a similar way. So let's have a look at Sonic Pi has ones for things like octaves. So let's do that one. So it follows the same pattern, kind of got a name, which is Octs, which defines the data type, as it were, or which defines what type of ring this is. We give it a pitch, let's say we give it C2, and then the number of octaves that we want, we add a number. Let's say we want 3. Make a live loop for those. Give it a sleep value. And now iterate through my Octs. It's a tick. And that's it. Change the release. Get a little bit shorter. 0.3. Make it a little bit quicker. Now, accessing it as a tick isn't really as interesting, probably, as maybe using choose. That kind of extends the idea. Okay, see you on the next one.